I passed out to y'all these Science Without Borders flyers. I think I was told there's an informational meeting on the 14th of November. If you came in late and you didn't, if I didn't get you one of these, you see me after class. I've got plenty of flyers here for you. Remember, exam 2 will take place Friday, like next class period, 9 a.m. to 10 a.m. We'll have a review tonight or this afternoon at 5 o'clock upstairs in 203. Okay. The floor is yours. Questions? Yes.
You go over those questions where it gives you a set of polynomials and you ask whether or not it's vector space.
Is this the most recent quiz or is this an old one?
This is like the first cover. Vector spaces.
Okay, so yeah, I don't have all the quizzes posted yet. I'll do that after class, but let me ask you guys a question. After you all have taken the quizzes, whether you've taken them or not, can you look at the quiz itself, the questions on there? Okay, so you just click, okay, good. So is there something that you can tell me that you want me to look at? I can pull something up. I'll call it hands. Did you figure out what the quiz that was?
Not yet. That doesn't sound- I guess quiz 13.
Quiz 13.
It looked like it.
Okay, so this is from quiz 13. Is this like that first one where we're looking at all the? Thing. Okay, so. C is a collection of all continuous functions. Mod R. Which are subspaces. So we're assuming at the outset that continuous functions are a vector space. I didn't ask you to show this, but I'll talk you through it, right? What happens, so this is like a calculus problem, really. What happens that you learn in calculus? What happens when you add two continuous functions? What do you get? So continuous functions are our vectors. You add two vectors, you get a new vector, right? What happens when you take a continuous function, you scale it, you multiply it by a number? Right, sine x is continuous, so 5 sine x is continuous, and -7 sine x is continuous, right? So this is the makings of a vector space. The zero function, continuous, right? And that's the zero of our vector space. When you add functions, it's associative and all that jazz. I really mostly only care about the zero and the close. Now for subspaces, we only have to check 3 things, right? So I've asked you on all these. Which are subspaces, and the first is the set of a set of f of x continuous such that the integral from -1 to 1 of f of x dx is equal to 0. Now, we're looking at all continuous functions that have this property. And there's lots of them. I mean, how about that? The integral from -1 to 1 is 0, right? How about that? How about that? How about, and I'm never going to get this right, but there's a little positive, maybe a little need more like that. who knows, right? That's probably not right, so maybe I should. Anyway, what a beautiful drawing, is it not? But the idea is the positive area and the negative area are supposed to cancel out. That's all you need, right? Now, is this a subspace? Actually, it is. We gotta check for three things. Zero is in there. What's this? Zero. You integrate zero, one, minus one to one, you get zero. So the zero function is in there. Ding, 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 there's one, right? Two. Suppose f of x and g of x are in, then the integral from minus one to one, minus one to one, f of x, and the integral from minus one, g of x are both zero, correct? Well, let's look at the integral from minus one to one of f of x plus g of x. Well, I don't know much, but if I can integrate two functions, I can break up the integral. And all these functions are continuous, so you can integrate them all. Any continuous function, integrate it. How about that? So f of x plus g of x. Is in the set. And the last thing we have to show is any multiple of f of x in the set. All right. So Roman numeral 3, if suppose you have a constant, then a constant times a function has interval 0. So C f of x is in. So yes. This is a subspace. Everybody agree? Right, okay, so what's the next one? You talk to me.
Yes.
What's the next?
I think there was another one after that where it wasn't subspace.
Right. Two. Set. F of x and C with. Subspace? No, why not?
Doesn't pass through zero.
That's the easiest way to do it. Zero's not in here, right? No. End of story. It's also not closed under addition either. Because if you have a function whose integral is 1 and you add it to itself, the integral of that will be 2, right? Or if you multiply this by 3, the integral will be 3. So everything fails for this one. Am I okay with that? Yeah, this one's a big fat out. How about this one? So. And here, I am going to skip over the calculus. We're not gonna. Y'all remember doing improper intervals? You actually have to integrate this from minus s to 0 and 0 to t and let s go to infinity and t go to infinity. I'm just gonna treat this like a symbol, right? Because we all know calculus to some degree. So, What about this one? Is this subspace?
No.
Okay. Let me give you something that's complete. This is absolutely complete. I wouldn't expect you to place this far, but let's take this apart. Where does this fail? What does it have? And actually, that's the only thing that fails, right? Because is zero in here? Well, when you integrate zero to minus infinity to infinity, it's zero, right? So zero is in here. And if you have two things that have a not negative integral answer, when you add them up, it's gonna still be a not negative integral. Everybody agree with that? The scalar multiplication is what fails. And this is really kind of stupid, but the thing that you might ask at this point is, are there any functions at all that integrate to something positive other than zero? Well, something non-negative other than zero. Right, it occurs to me that there may be nothing in the set other than the zero function. If zero was the only thing in here, this would be a subspace, right? Is there a function that integrates to a finite number that's greater than or equal to zero that is not the zero function? Yeah, you're exactly right. He's too smart for me though. I need something easier, right? My piece out of the brain. But yeah, he's right. The normal distribution function, e to the minus x squared, you got to change it by parameters, whatever, but we do this. Notice that the integral from minus infinity to infinity. You gotta remember what the antiderivative of this is? Yeah, that's right. And this is pi over 2 minus pi over 2, which is pi. And pi is of course greater than or equal to 0, but not 0. So f of x but well, the integral from minus infinity of minus f of x minus pi plus it's not subspace. It was almost a subspace. It only failed by the scalar multiplication. Anybody? And the last one was right. The collection of all things with a finite interval. This is all the stuff that you can integrate and you get a number, be it positive or be it negative, or whatever that number is, its absolute value is finite. Is this a subspace? This one actually is. Let's go through it. No problem with the zero function, right? Number two, if the integral from minus infinity to infinity And the interval from minus infinity to infinity of g of x is m. So suppose f of x and g of x are two things that live in here, so they've got finite intervals. What is the interval from minus infinity to infinity of f of x plus g of x? It is. It is n plus m. And this is also finite. And the final thing we have to have is you have to have a constant underneath functions in here. What's that going to be? So, yes, you got zero, close under addition, close under scale. Okay. Did that answer your question, or did you want me to do two as well?
No, I'm good now, thank you.
Okay, any questions on this? Okay, yes,
Could you actually do two?
yes, absolutely, sure. Let, so let me write down the rules of the game here. So we're gonna let p of x all polynomials with real coefficient. Okay, actually, I'm gonna do more than just this problem, because I referred back to an earlier one, I'm gonna make sure all that. First of all, let me ask you just a question about this. You know, we've done stuff with P2 and P3 and PN, things like this. This is just plain old P, there's no restriction on the degree, right? As a vector space, as a real vector space, what's the dimension of this?
N plus one. Oh, infinity.
It's infinite, right? Because there's no restriction on the degree. Can anybody give me, what's the easiest basis you could think of probably for this? One. Yeah, the powers of x will all work, right? And that's certainly an infinite basis, right? It never stops. So this is an infinite dimensional vector space. Now, I refer back to a couple other problems. So let me point out, actually, the previous problem that I referred to, we did this with finite polynomials. We'll do this. First, we'll let D. This is going to be my derivative operator. What happens when I take derivative of a polynomial? What do I get?
Must agree.
Right, but I still get a polynomial, right? I mean, I don't get sine x or anything like that, right? I take derivative of polynomial. I'm going to define this thing here, and I'm going to claim it's linear transformation. Input, polynomial, output, take its derivative, new polynomial. I'm going to prove to y'all that this is a linear transformation. What do I need to do to show it's a linear transformation? Well, close is not quite the right word there, but yeah, it has to behave well for addition. It has to respect addition and respect scalar multiplication. So what we need first is something like this. These, of course, have been here two polynomials. What does this rule say? It says, hey, take my derivative. Okay, so I'll take your derivative then. Now, let's pull through the years of therapy and think back to the calculus days, right? What happens when you take the derivative of something like this? That's right, and this sounds like an old calculus exercise. What is this? This is that prime of x. What's the prime of x? This is one of our first sort of derivative rules, right? And what is this? This is, first piece is df of x, and the second piece is dg of x. And there you go. It respects addition, so it's linear on the addition. We gotta convince ourselves that it preserves scalar multiplication. So again, this is saying take my derivative, which I will do. And what's the thing that we can do with constants? Pull it out. So this is C. Rule one, rule two satisfied. There you go. It's a linear transformation. Right? How many of you ever heard, oh, the derivative is a linear operator? Did anybody ever hear fancy words like that when you're in calculus? Right, and they don't tell you about linear transformations usually back then, but that's what you mean. Yes.
How do we prove on a test that it also contains the zero vector? Can we just state that, like?
You don't need it for linear transformation. It is a consequence. So for a linear transformation, what is true is, say you have a linear transformation, we'll call it D, just like this one. D of the zero vector is always zero vector. But you don't ever have to show that. It is a consequence of this. Because to show that, all you have to do in this thing is take C to be zero. You have D of zero is zero times whatever this output is. So if you're trying to show something's a subspace, you need to show that the zero vector is there. What you're showing is that there is something in the space. For the linear transformation, you give that all a miss. It's not wrong for you to show that D of zero is zero, but it's unnecessary and it's wasted your time. Yes.
So did you say that it has to behave well under addition and scale multiplication?
Right, it has to respect the addition. So D of the sum is the sum of the D's. Right.
How is that different from closed under addition?
What closed under addition means is if I have two things that live in a particular zoo, then when you add them up, the sum lives in that particular zoo. This is a slight difference. It's very similar to what you're talking about, right? This is why linear transformations are studied with vector spaces, because this doesn't mean closed. F of x plus g of x is still in this vector space. This isn't closed. This is the way it's behaving with respect to this function. But these rules are precisely because the vector space has those. That's why we pay attention to these kind of transformations.
Sort of look like if it wasn't behaved.
Perhaps, like, for example, sine of x plus y, right, is not sine of x plus sine of y, right? This is a kind of a big trigonometry, and sine is not a linear function. It doesn't behave well, with respect to, vector spaces like that. Okay, other questions? Okay, the integral is a linear transformation as well. And here I mean the definite integral. And let me, this actually is an indefinite interval, the particular constant. I'm going to define I from dx Again, input polynomial, output polynomial. So sometimes this is a little bit less familiar. Let me remind you. So, for example, what is this? This is a particular antiderivative of this. So let's go through the motion, shall we? What's your favorite antiderivative? 3t squared. Antiderivative of 6t. 6. How about 3t squared? It's been a while, hasn't it?
Yeah.
I like this because you can always check it. Derivative of this, three t squared is 6 equals 5, so I'm good to go. Right. We're evaluating this from 0 to x. Plug in x, I get x cubed plus 3x squared plus 5x minus plug in 0, I get 0. So you might think of this really as the antiderivative of the function with constant 0, right? Because the general antiderivative is this thing plus a constant, right? The 0 actually figures out what the constant needs to be for it. Everybody cool with that? Okay, so I'm gonna test, this is linear transformation. So let's rules, let's do our rules. This is the interval from 0 to x of f of t plus g of t. I don't know much, but what can I do with intervals? With them, I can split them up, right? If they're both integrable, which they are. Split the interval, and this is I f of x plus I. There we go. So it works with respect to our first rule. It respects the sum, right? And what can I do with constants? Hold on. So this is stated. So there we go. It's linear transformation. Okay, so I have demonstrated that both D and I are linear transformations from PX to PX. So a question is that it says determine if the linear transformation D is 1-to-1 and determine if it's onto and justify your answers. What do you think? Is it 1-to-1? Is it onto? Is it both? Is it neither?
It's onto, but not 1-to-1.
What's that now?
It's onto, but not 1-to-1.
Yeah, I think that's right. I think that's right. It's probably easiest to see why it's not 1-to-1. What does it mean to be 1-to-1? It means any two different inputs have to go to different inputs, right? Can you think of two different inputs to a derivative that are different but give you the same output? Yeah.
X and X plus 1.
That's a great example. What's the derivative of x? It's 1. But isn't this also the derivative of x plus 1? Okay, there you go. And these two are different, so not. It is onto though, I think. How do we do that? So that it's,
Degree input, get an output of degree n minus 1.
okay, so. On I don't know much, but this is what a typical polynomial should look like, right? Where these are real numbers, A0 plus A1x plus A2x squared, all the way up to A and X. Now I need something that goes to it. Onto means that thing has to have a dance partner. There's somebody whose derivative is that, you know, in a candidate. I need something that when I plug it into D is gonna spit out this. Okay. So let's take the antiderivative. Actually, any antiderivative will work. And by the way, there's a lot more g of x's I could have, because notice that I let the constant be 0, right? I just made that up. I could let the constant be 2 or square root of 2 or 8675309. It doesn't matter. Any constant, its derivative will be the same. So if I look at d of g of x, this is g prime of x, which is a0 plus a1x plus a2x squared, all the way up to a n x n, which is f of x. So on to. What else? I asked the same two questions about ix. Let's look at that. What do you suppose? 1 to 1, is it on to, neither, both? Same? So are you saying not 1 to 1, but on to?
Yes.
Try flipping that.
So it's 1 to 1, but not.
Yeah. So. I of x actually is 1 to 1. Let me show that. Suppose. Suppose I find two polynomials. I'm gonna call them f and g. And suppose when I plug these two polynomials, I get the same answer, right? That's what I mean there. I of f of x, it gives me something, it gives me the same thing that I of g of x had. What do I need to verify to show that this is 1 to 1? You have to show that f of x and g of x have to be the same, right? This should force f of x and g of x to be the same. Well, is everybody with me on the 1 to 1-ness? This is what our goal is. Is everybody clear on that? And we need to show that if you have two inputs that give you the same output, those inputs had to be the same. Okay, so let's see what happens here. Let's write down what this is. Oops, see? It's equal to. Anybody want to guess what the next step is? Right. Those two things are equal. Let's just take their derivative and see what shakes out. What is the derivative of the integral from 0 to x of f of t dt? Yes, this is a fundamental question. This is the first fundamental there in calculus. This is f of x. What's this? So the inputs had to be the same. How about that? Okay. Everybody okay with it? It's not on to that. Let me just look at what a typical thing looks like. So if f of x is written in this form, then this is the integral from 0 to x of a0 plus a1t plus a2t squared plus n. Let's go through the work that we did last time. This is a0t plus 1/2 a1t squared plus 1/3 a2t cubed. 1 over n plus 1, a n bn plus 1. Give it x. So let's plug in x for this. And when I plug in x, I get a0x plus 1/2 a1x squared. It's 1/3 a2x cubed plus 1 over n plus 1 a n x n plus 1 minus what I get when I plug in 0. What happens when I plug in 0 to that sucker? What do I get? Everything falls out, I get 0. Everybody agree? So I'm done. Agree? Now, this is what a typical output of this function looks like. Does that help you discern why this is not onto? Does anybody see a polynomial and there's no way that it can be of that form? Make it simple. Right, right. That works. What do you notice about this? What do you notice about this polynomial? What's true about the constant term of this polynomial?
Always 0.
Constant term is always 0. Notice that. 1 plus x, 2, 7, 3 plus x squared. None of these range of I. So not on. This thing never produces a polynomial that has a non-zero constant. Any questions on that? Question? Yes.
Could we just say that the degree of the output is 1 greater than the degree of the input, so it can't be onto?
Yeah, so in particular, so the degree of the output is 1 greater than the degree of the input. Almost always. Except for 0, right? And so in particular, you can never have an output that is a degree 0. So you can never have a non-zero constant term. Yeah, you can do that. Okay, other questions? Okay, how about other questions in general? Yes,
Number 5 on fall 2022 exam.
fall 2022. Okay. This, of course, you need exam 2, right?
Yes.
Fall 2022, problem 5. Okay, so problem 5 says, suppose, okay, this is kind of a fun problem. Suppose you have an n by n invertible matrix A. So let me give you the setup here. A is n by n and invertible. And it has this property here. A times A inverse is equal to something, A squared. Find determinant of A, or explain why there is not enough info. Of course, here I mean a real matrix. Okay, any ideas on this? So we either gotta figure out determinant of A or explain why there's not enough information. Any ideas? What we might do?
Well, my thought was that if you can get the a to the negative one on one side, you can use that that's equal to one over the determinant kind of.
Right. That sounds like a great idea. Well, let's do that. And the way that we get it over to the other side, so to speak, is let's multiply on the right by A. Right, okay. Now, what I have on the right side is A cubed. What do I have on the left? I'm tempted to say A. All these, that equation is ridiculous. Somebody tell me why. That's right. This is a matrix. A matrix cubed is a number. That doesn't really make any sense, does it? Unless the matrix is one by one, right? Then it would make sense. But this is an n by n matrix, so this should be A by n, because A inverse times A is the n by n identity, and that makes me a little bit more comfy. Okay, so I did say n by n, didn't I? Right. You know.
A cubed and a diagonal.
Oh, okay. So actually, what does this matrix look like? That's a good observation. A. I agree with it. Okay, so what I would suggest is take the determinant. I agree with it. And by the way, what's the determinant? What's this right here?
Eight raised to n,
What's it, 8?
8 raised to n.
That's exactly right. Everybody agree? This 8 being found. What about this? Well, there's an important theorem about matrix multiplication and determinants. What is the determinant of A times B? I have two n by n matrices. It's determinant of A times determinant of B, so you can break this up. So this should be the determinant of A times the determinant of A times the determinant of A. Agree? So this is actually determinant of A cubed. And I'm gonna make my life a little bit easier. This is 2 to 3 n. Right? 8 to the n. Now I gotta do is take the cube root. There's no ambiguity here. Determinant of A is 2 to 3. Everybody okay with it?
So that's enough information to just answer that.
Yeah, that's exactly what it has to be. Can somebody give me an example where we might work an equation like this, an example where you might not have enough information? What if you come up with this? Different problem, but what if you come up with this? Let me put something here. Can't tell me exactly what it is because this could be plus or minus, because this is an even power. So there's a little bit there to get here. But when you take cube roots, the only cube root of a positive real number is just a positive real number. The other two are imaginary, or which can't be the determinant of a real matrix. Not imaginary, complex, but not real. Okay. Everybody clear on? Yes.
So, when you added in the, identity matrix, it's just safe to assume that you have like a constant, equation is gonna be identity matrix.
Right, if you have so here's the little lesson for today, I guess. If you have an equation and one of the quantities is a matrix, it better all be matrix quantities. You can't have like the cube of a matrix equals 65, right? So you need to make sure that everything balances.
So essentially, like when you're multiplying, some constant by a matrix, you're essentially just multiplying a, identity matrix of that constant.
Okay, right. So what he's saying, so one of the things that we learned is this: if I have a constant times a matrix. So this is one of the rules that we taught, but you're right, it's a sloppy shortcut. Because one of the things you've learned is this C A11, C A12, C A1N, C AN1, C AN2, C ANN. This was the rule that we gave for multiplying constant by a matrix. You just multiply all the way through it, right? A more careful way to do this maybe is this is really the matrix C so it's just this is often called a scalar matrix because it is quote the scalar C times the identity matrix. It is the analog, it's the closest matrix to the number that you can get, right? It's the analog of that. Okay, other questions? Yes, sir.
Number 6 on summer 2018 exam 2.
Exam 2, number 6.
Yep.
Right, so, suppose you have a 2x2 matrix. Are you gonna be at the review session tonight?
Yeah.
Okay, this is probably, since it is 9:53, it's probably a little bit involved, but let me give you the problem. I'm gonna start it so we can finish it at the review session. You're given this matrix here. Cosine. It says, suppose there's a real number lambda and a non-zero vector such that A B lambda B. Show that the determinant is 0. Okay, so here's the setup. Show that A B is lambda B,
Another.
for some non-zero. Suppose there is a real number such that. Lambda. There we go. show the determinant of A minus lambda I. Okay, this one I can dispatch pretty quickly. If this is true. Correct?
I agree with that.
Now I'm fixing to pull this V out. Notice A is a matrix times V, that's a two by one vector, this is 2 by 1 vector. But if I pull this V out. Oops. This part doesn't make any sense because it's 2 by 2 matrix minus a number. So now I fix it. Now, what does this mean? If V is not 0, which is what we said here, then V is a non-trivial solution to homogeneous equation. A minus lambda I x is equal to. Everybody agree with that? If it is not, it's a, so what must be true about this? If the matrix has a and this is of course square matrix, if it has a non-trivial solution to the homogeneous equation, what's true about the determinant? Must be 0. And that's all we're looking for part A. We'll pick this up at the review section. We will see you all then.